In the heart of CERN's sprawling laboratory complex, Dr. Diane Eckhart stood before a whiteboard filled with equations, her eyes fixed on one particular line that seemed out of place. It was 2017, and what had begun as a routine investigation into quantum field theory anomalies had led her down an unexpected path. "It just does not make mathematical sense," she muttered to her colleague, Professor Chen Fanning. "Every time we run the simulation, we get the same inconsistency." The equation they were studying had emerged from the confluence of two seemingly unrelated fields of physics, quantum entanglement and spacetime geometry. For decades, physicists had struggled to reconcile Einstein's general relativity with quantum mechanics, the infamous problem of quantum gravity. But what Dr. Eckhart and her team had stumbled upon suggested something far more revolutionary. The story of this equation begins not with Dr. Eckhart, but 70 years earlier with Albert Einstein's geometric theory of gravity. In 1915, Einstein had transformed our understanding of gravity from Newton's force acting at a distance to a manifestation of curved spacetime. According to general relativity, massive objects like stars and planets create depressions in the fabric of spacetime, causing other objects to follow curved paths around them, what we experience as gravitational attraction. This elegant theory had withstood a century of experimental tests, from the bending of starlight around the Sun during a 1919 solar eclipse, observed by Arthur Eddington, to the detection of gravitational waves by LIGO in 2015. For all practical purposes, Einstein's gravity seemed complete. Yet at quantum scales, general relativity breaks down spectacularly. The mathematics becomes nonsensical when we try to quantize gravity, Professor Fanning explained during a department seminar in 2018. We get infinite values that cannot be renormalized using standard techniques. This suggests we are missing something fundamental about the nature of gravity. Theoretical physicists had proposed various solutions to this problem: string theory, loop quantum gravity, causal set theory, but each came with its own conceptual challenges. None had produced testable predictions that could definitively settle the debate. Until Dr. Eckhart's equation. What made her approach different was that it did not try to quantize gravity directly. Instead, it suggested that gravity might not be a fundamental force at all, but an emergent phenomenon, a macroscopic effect arising from microscopic quantum processes, similar to how temperature emerges from the average kinetic energy of particles. The specific insight came in 2016, when Dr. Eckhart was analyzing data from quantum entanglement experiments conducted at the University of Vienna. Physicists there had demonstrated that two particles could remain connected across space in ways that defied classical physics, what Einstein had famously called spooky action at a distance. What if gravity is not a force but a consequence of quantum entanglement across spacetime? Dr. Eckhart proposed in her groundbreaking 2018 paper published in Physical Review Letters. If every particle is entangled with every other particle to some degree, could the resulting network of quantum connections create what we perceive as gravitational attraction? Her equation, formerly known as the Eckhart-Verland entanglement relation, built upon earlier work by Dutch theoretical physicist Erik Verland, who in 2010 had proposed that gravity might be an entropic force emerging from the fundamental tendency of physical systems to increase their entropy. Dr. Eckhart extended this framework by incorporating quantum information theory. The mathematics was beautiful and elegant. On one side of the equation was the familiar gravitational force term from Einstein's field equations. On the other side was a complex expression describing the degree of quantum entanglement between any two regions of spacetime. When applied to everyday objects and cosmic structures, the equation reproduced all the successful predictions of general relativity. But in extreme conditions, near black holes or in the early universe, it predicted subtle deviations that could potentially be measured. If Dr. Eckhart's theory is correct, noted Dr. Mark Wilczek of MIT in a 2019 commentary, we would not need to quantize gravity because gravity would not be a fundamental force to begin with. It would be a manifestation of quantum entanglement, which we already know how to describe quantum mechanically. The implications were profound. If gravity is merely an emergent phenomenon, a secondary effect of more fundamental quantum processes, then our entire conception of space, time, and matter would need to be reconsidered. Think of it like temperature, Dr. Eckhart explained during a public lecture at Cambridge University in 2020. Temperature is not fundamental, it is what we experience when atoms and molecules move faster or slower. Similarly, gravity may be what we experience when the underlying quantum entanglement network changes its configuration. This revolutionary perspective gained unexpected support in 2021 from experiments with quantum systems in laboratories around the world. At Princeton University, researchers demonstrated that entangled quantum bits, qubits, arranged in certain configurations exhibited behavior mathematically identical to gravitational attraction. The more entangled the qubits became, the stronger the effective gravitational force between them. We created a gravitational analog without any mass involved, explained Dr. James Marston, lead researcher on the Princeton experiment. Pure quantum information processing mimicked what we traditionally think of as gravity. The theoretical framework also offered elegant explanations for long-standing cosmological puzzles. Dark energy, the mysterious force accelerating the universe's expansion, could be reinterpreted as a large-scale manifestation of quantum entanglement across cosmic distances. The accelerating expansion began approximately 7 billion years ago not because some new force switched on, but because the entanglement network of the universe reached a critical threshold. Even dark matter found a natural explanation within this framework. The apparent additional gravitational effects observed in galaxies could be attributed to enhanced quantum entanglement in regions where normal matter is concentrated. The beautiful aspect of this approach, noted theoretical physicist Dr. Nima Arkhani-Hamed of the Institute for Advanced Study, is that it unifies phenomena we previously thought were separate. Gravity, dark energy, and dark matter may all be different manifestations of the same underlying quantum entanglement structure. By 2022, the scientific community was divided. Many physicists remain skeptical, pointing out that while the theory made compelling predictions, definitive experimental proof remained elusive. Others embraced the new paradigm enthusiastically, seeing it as the breakthrough that could finally resolve the century-old conflict between quantum mechanics and general relativity. Science advances through radical reconceptualizations, observed physicist and science historian Dr. Sarah Johnston. Just as Einstein showed us that gravity is not a force but curved spacetime, Eckhart's equation suggests that curved spacetime itself is not fundamental but emerges from quantum entanglement. The most dramatic test of the theory came in 2023, when the Event Horizon Telescope collaboration released new observations of the supermassive black hole at the center of our galaxy. Their measurements of how light behaves in the extreme gravitational environment near the black hole matched the predictions of Dr. Eckhart's equation with remarkable precision, including subtle deviations from general relativity that Einstein's theory could not explain. But perhaps the most profound implications extended beyond physics into philosophy. If gravity emerges from quantum entanglement, and quantum entanglement represents information connections between particles, then in a sense, the force holding the universe together is information itself. The physical universe may be more like a vast computation than a collection of objects, proposed philosopher of science Dr. David Wallace. Mass, energy, space, and time might all be secondary features emerging from a more fundamental reality composed of quantum information. This perspective resonated with ancient philosophical traditions that had long suggested the material world might be an illusion hiding a deeper reality. But unlike those traditions, the new theory offered mathematically precise, experimentally testable predictions. For everyday purposes, Newton's laws would remain perfectly adequate for calculating planetary orbits or the trajectory of a baseball. Einstein's general relativity would still be essential for GPS satellites and understanding black holes. But at the deepest level, gravity would be understood not as a force or even as curved spacetime, but as a manifestation of quantum connectedness. If this theory proves correct, Dr. Eckhart reflected during a 2023 interview, we will not have made gravity obsolete in practical terms. Apples will still fall from trees. But we will have transformed our understanding of why they fall. The equation does not promise anti-gravity technology or science fiction propulsion systems, at least not immediately. But it does suggest that by manipulating quantum entanglement patterns, we might someday influence gravitational effects in subtle ways, possibly leading to new technologies for space exploration or energy production. More importantly, it represents a fundamental shift in how we understand reality itself. Throughout history, humans have gradually discovered that many apparently distinct phenomena are actually different manifestations of the same underlying principles: electricity and magnetism, matter and energy, space and time. The Eckhart equation suggests another unification: gravity and quantum entanglement. As we venture deeper into the 21st century, this revolutionary idea continues to be tested and refined. Whether it ultimately proves correct in all details remains to be seen. But it has already succeeded in challenging our assumptions and expanding our imagination about the nature of the universe. The most profound scientific revolutions do not merely solve existing problems, they change the questions we ask. If gravity is indeed an emergent phenomenon arising from quantum entanglement, we may need to reconsider what we mean by fundamental in physics. Perhaps the true fundamental building blocks of reality are not particles or fields or even spacetime, but patterns of information and their relationships. In this view, the equation that could make gravity obsolete is not eliminating a force from our understanding of nature, but elevating it, revealing gravity to be not merely a physical interaction, but a glimpse into the informational substructure that underlies all of reality. As quantum physicist John Wheeler once suggested, perhaps from bit, the physical world emerges from information. And if that is true, the universe is even stranger and more wonderful than we had imagined.